Good morning, class. Or if it's the afternoon, good morning, good afternoon, classes. This is Mr. Shelton. As you know, I'm out because I'm with my father in the hospital, but we still have things to do. So, this video is going to be the instruction for today. It is concerning something called relative velocity. So, in your notes, if you haven't already, you get a new section called relative velocity. I'm going to go over the basic idea of relative velocity. I'm going to work a couple of sample questions. And on EDSP, there are 3 or 4 practices for you to try and work out. It's not a particularly challenging idea, and it's something that you kind of already do. But if you've never done the actual math behind it, it can sometimes be an issue. I'm going to show you 2 things about it. I'm going to show you the basic idea of what's happening, and then I'm going to show you a kind of a procedure on how you can ensure a correct solution every time, no matter how complicated it is. So we're going to start with a one-dimensional idea, which is not particularly interesting, but at least is the kind of idea that you can wrap your mind around because you've probably seen something similar before. But believe it or not, this is a truck. All right, there's a truck, and you have a friend standing in the back of the truck. You are standing slightly off the road. Your friend decides to throw you a ball, and they throw the ball at you at 5 meters per second. How fast is the ball going when it reaches you? Well, I don't think anybody in the room here has a problem with the idea that the ball reaches you at 5 meters per second. Now, what if instead they throw the ball? There you go, getting all this out of the way. What if instead you stand in front of the truck, but slightly off to the side, so you don't get hit, and they throw that ball forwards at, say, 10 meters per second? Any problem with the idea that when the ball reaches you, the ball's going 10 meters per second? This shouldn't be too big a deal. They threw the ball at 10 meters per second. It reaches you at 10 meters per second. It's the horizontal velocity. There's no acceleration. But what if instead the truck is moving forwards at 5 meters per second, and then they throw the ball forwards at 10 meters per second? The idea here is that when the ball reaches you, it already had the velocity of the truck, and then the person gave it an additional velocity. So that when the ball reaches you specifically, it's already got the 10 meters per second of the person throwing it plus 5 meters per second of the truck, so that the total velocity is 15 meters per second for the ball when it finally reaches you. Now, I think your intuition will tell you that that's no big deal. What you see on the bottom of the page here is that I've added the 2 vectors together, and I've done so in what's called graphical addition of vectors, where I took each vector and, attempting to draw them to scale, I added them tip to tail. So I added the white vector first by itself, and then I added the red vector directly afterwards by putting the tail of the red vector at the tip of the white vector. The green vector represents the resultant from adding together those 2 velocity vectors. Now, the thing about adding together vectors is that you have to take into account the direction of the vector when you add them. That's the most important idea. Like, the truck doesn't have to be going forwards. I think you can all imagine that there's a situation where the truck is traveling backwards, or at least maybe not backwards, maybe just in the opposite direction of where you're standing. So you might be standing over here again. Truck is over here. truck is traveling this way, 5 meters per second. In fact, let's continue to use the same colors there. That way at 5 meters per second. You throw the ball to your friend backward to 10 meters per second. This time, when the ball reaches you, although you threw the ball backwards at 10 meters per second, the fact that the truck was traveling in that direction at 5 meters per second, that's going to be a little different, isn't it? This time, the resultant vector has to combine both the forwards motion of the ball and the backwards motion of the truck. When you draw your resultant, you start where the first vector began, and you end where the last vector's tip ends. So our actual resultant looks like that. So you receive the ball at 5 meters per second. Why? Because 10 minus 5 equals 5. Now, doing this in one dimension is no big deal. I could give you walking directions. I could say walk in the positive direction, say 25 meters, and then walk in the negative direction, 10 meters. Well, if you want to draw that out, we'll make the first one the white one and the second one the red one, so that I get, okay, my first vector is in the positive direction and it's 25 meters. My second vector is in the negative direction and it is 10 meters. So my resultant, starting from here, ending here, is going to be 25 minus 10, or 15 meters. That's the resultant. One-dimensional is not so tough. But what if I said instead, and this is where this whole thing gets a little bit more complicated, interesting, you use your word. What if it was the positive y direction, 25 meters, and the negative x direction, 10 meters? There's absolutely no reason why we couldn't do this in 2 or 3 dimensions. When you start getting here, the problem becomes a little more complex, requiring you to, especially graphically, take a moment to draw out what actually must be happening to both the y direction and x direction of the object's motion. These are displacement vectors. So the first one would have me draw it from the origin. From the origin. I want to go in the positive y direction, 25 meters. Notice that I'm kind of establishing the scale as I work. Then I have to go in the negative x direction, 10 meters. My resultant still requires that I start here and draw a vector that ends at the tip of the other vector. Now this is carefully crafted, but you'll notice that kind of by design in this one, we got a right triangle right there. And we've been doing all that work in right triangles. Your job now would be to find the size of the resultant vector. I couldn't just guess at it. I know it's going to be bigger than 25 and 10, but it's going to be less than 25 plus 10. You know, I'm probably going to use something like 10 squared plus 25 squared. Yeah, use that to figure out what the actual size of the vector is. So you work it out and you get 27 meters per second. I'm sorry, not meters per second. 27 meters. That's how far you have to walk. Now, if you walk that green line, you're definitely going to be walking less than if you walk the red line and then the white line. But the idea here is that this is the result of your two other displacements. It gives you a third displacement that represent the resultant of walking those two. Now, you wouldn't actually be done here. You'd also need to find out what this angle is. This angle seems to be relative to the y-axis, but I can find that angle by looking at, I think the tangent function will do it for me. It says tan theta is going to be opposite over adjacent. So grabbing a handy dandy calculator, let's see, 10 divided by 25. Looks like it's 22 degrees. Now, 22 degrees really isn't my answer. We have to give reference. So I would probably say it's 27 meters, and I could count this 90 degrees first and then add the 22 to it, and then give me 112 degrees from the positive x-axis. We'll talk more about reference when I'm there, but if you can get this and this, you're doing good. So what might a problem like this look like? And I'm being honest, this is the simplest way these problems can come. They can be harder, but let's look at the simplest way this problem can come. Maybe you're at a river and you know that the water is going by at 3 meters per second. It's pretty fast water. And you're gonna try and go from one side of the river to the other side of the river. Let's say there's two docks that are directly across from each other. So you're going to take your boat and try and paddle straight across. And let's say your paddling speed in the water is 4 meters per second. If you try and paddle straight across, are you actually going to land at the dock on the other side? And you guys all know that no, you're not. You're going to try and paddle across, but your boat is going to drift to the side. So maybe you want to find out, what is your actual velocity? Your velocity relative to the shore. That's what we call this relative velocity, because there's your velocity relative to the water, but then there's your velocity relative to the shore. So when you include both your velocity and the water's velocity, you get the relative velocity of a person who is witnessing you attempting to travel across the river. So, just like any other time, if we want to add vectors together, just the graphical portion of this tells me that I'm going to have my velocity plus the velocity of the river is going to give me a resultant vector that's going to come from this triangle, with this likely being my resultant speed. Doesn't tell me direction, but it tells me how fast I'll be going. It'll be me plus the water. And this is a 3, 4, 5 right triangle, so I might have to do any calculation. I'm going to be going 5 meters per second. But if I want to know the angle that I'm traveling, well, then I'm going to have to do a little more work. Looks like I'm going to have to use the tangent again to get 3 and 4 and figure out that it's 37 degrees. Now, this one's a little harder when it comes to like figuring out how I want to write this. And again, we're going to talk more about reference when I'm there. But if I really wanted to tell somebody what direction I traveled, just saying 37 degrees wouldn't be enough. I have to give reference. 37 degrees compared to what? Maybe it's 37 degrees compared to north. If that way is north, then by consequence, this way is probably east. I'm actually traveling 37 degrees east of north, right? because I'm starting from the north and turning 37 degrees towards the east. So I am east of facing north. If you can't do this part yet, that's all right. It'll take some time. Now, the truth is, this sounds great, except that now my boat is drifting off course. I'm going to land over there. I'm not going to land at the dock. I mean, relative velocity problems typically, don't want to just give you the possible result. They might want you to fix the problem. I mean, you probably understand that what I'd rather do is find a way to go straight across the river, not go across the river and land in the wrong spot. If I want to go straight across the river, is it clear to most of you that the best way to do that would be to kind of paddle into the current some? Well, this isn't arbitrary. If I know the river is going 3 meters per second to the east, and I know that I can paddle at 4 meters per second, how do I figure out how to get straight across the river? I mean, I want my result to be due north. Well, we can still work that out. In fact, it's largely the same as what we did, except I know I'm probably going to have to paddle this way, paddle into the current some. I know I can paddle at 4 meters per second. So I want to make sure I turn with enough of an angle so that the river pushes me back so that I'm straight on course. River pushes me back at 3 meters per second. Now what this means is if you actually were to do this, if you actually line this up just right, your boat would face this way the whole time you're traveling until you made it all the way over to the dock. You'd be facing this way the whole time, giving some of your vector for your velocity north and some of your vector for velocity west into the current so you could safely navigate across. What we've drawn is simply a sketch of what we think the result would look like. Now, if we want to actually figure out the angle that we have to face to do that, our actual heading that will take us across the river, we just need to solve this triangle. Now, my sketch is me trying to interpret what has to happen for us to effectively cross the river. It's not in and of itself perfect, but it gives us an idea. But the trig, we can do the trig to figure it out. For example, if I want to figure out the angle, and I look at the trig I have there, I'm going to note that this is the opposite side. This is the hypotenuse. So sine of theta is going to be 3 over 4. This is going to help me find out how many degrees I have to face in order to get myself oriented correctly. So let's see, 3 divided by 4, and then do inverse sine. Inverse sine tells me that I have to face 49 degrees. Theta has to be 49 degrees in order for me to effectively make it across the river. So my sketch isn't very well to scale, is it? In fact, if I really wanted to see what that would look like, 49 degrees, heck, that would be like, that would have to be 4, and that would be 3. That's a better representation of what's happening here. And my result, my result's going to be from here to here. Right, that's going to be the actual vector of my velocity. If I want to figure that out, got to be careful. That's going to be 4 squared equals 3 squared plus adjacent squared, right? If this is the adjacent side, then that's how I'd figure it out. So this is going to be the square root of 4 squared minus 3 squared. That's going to equal a. So let's see what I get here. 4 squared minus 3 squared. Take the square root. 2.7 meters per second. So even though when I paddle a boat in still water, I can paddle at 4 meters per second. With a current of 3 meters per second, if I want to make it across the river directly and I face into the river the amount I have to face, then I'm only going to progress across the river at 2.7 meters per second. This is because I'm having to fight the current to get across the river. And these are relative velocity problems. They generally require a straightforward um, picture to try and get an idea of what's happening. And if we've been fortunate enough, the picture will include a right triangle. And that way, we can use that right triangle to find our answer. Now, unfortunately, it's not always so simple. In fact, you could probably imagine a problem where it's not true. What if you have a plane that's flying in the wind and it's traveling at 100 kilometers an hour and it's traveling at an angle of 63 degrees when compared with east, and the wind is blowing the plane this way at 30 kilometers an hour. I guess I've been making these red, so I'll make that one red too. They're 30 kilometers an hour, and it's at an angle of negative 50 degrees compared to the east. And then the result of your plane's flight is going to be something like that. There's no right triangle here anywhere. These would be tough if I want to figure these out. Because I'm having to add them. I don't have a clear right triangle that I can use to kind of figure out how to get the resultant. Even worse, if I want to try and find a plane in a specific direction in order to go a certain way, you can imagine that these would be even harder. So we're dealing with some kind of specific ones that automatically kind of form a right triangle for us, but they don't have to be like that. They can be more complicated. So if you can't see your way to kind of set up a right triangle in your answer, like if you can't draw one out that already has a right triangle somewhere in it, then it's going to make the problem much more difficult to solve. You're going to need a plan. So one of the ways to do this is by converting your vectors from the notation that you've been given to rectangular notation. What I mean is the vectors we see right here are all given to us in what's called polar notation. Polar notation gives you a length and a direction. This is compared with rectangular directions. Rectangular notation gives you two components, an x and a y. It's just two different ways of writing a vector. The thing is, as I've said before, our class is always one-dimensional, which means we know how to add up individual x components and individual y components. We don't know how to add up vectors that look like that. So if we are given vectors that are complicated, that are in multiple directions, that don't make a perfect right triangle, then in order to solve those problems, we have to first convert our vectors to rectangular, add the rectangular components together, and then convert our answer back to polar. Now it's not easy. We're going to do an example of this so you can get an idea of how to do it. But this probably represents more than what you're going to have to do on the exam. The first two problems we saw, yeah, with the river, you can do that. But this one, a little more complicated. So what we're going to do, we're going to take a plane flying. I'll make the plane easy. Due north at 100 kilometers an hour, and combine it, we're going to add it to the wind that's blowing. And here we go, we're going to add something to it here. 30 degrees north of west at 25 kilometers an hour. So those are our two vectors. Now, I'm going to continue to try and draw what's happening here. But I'm also going to recognize that I have two vectors and a result. The plane, which I'm going to put in red, is going 100 kilometers an hour due north. Just like that. The wind, on the other hand, I want to add the wind. To add that vector gets added right there to the tip of the first vector. And it's 25 kilometers an hour, 30 degrees north of west. Well, west is that way. North is that way. 30 degrees north of west. So I start at the west, and then I turn towards the north 30 degrees and draw my vector from there. So my result will be from here, the beginning, to here, the end. How do we do this in practice? Well, to do this in practice, we're going to take the plane, break it up into X and Y. The wind, break it up into X and Y. And then we're going to add those two components together to get the result. So it's kind of like a chart. We're going to have the plane's X and the plane's Y, the wind's X and the wind's Y. Add them together, and we'll get a resultant vector. Now, it's not straightforward, and it takes some real kind of convincing, but let's look at each vector by itself. The plane is the easy one. The plane is due north. It's in the positive Y direction, no X. So I can just put 0 and 100. That's the plane, because the plane is going in only one of the dimensions that's there, the positive Y dimension. The wind, not so much. So to do the wind, I'm going to get the wind by itself. I'm going to chart the wind. I have 12.5 in the positive Y direction and negative 21.65 in the X direction. Now, I've broken both vectors up into components. Now I need to add them up. 100 plus 12.5 will be 112.5 in the Y direction. 0 plus negative 21.65 is negative 21.65 in the X direction. This is the result of the wind and the plane. If I want to find the just the wind. I'm going to go over here by myself. Whoops. Go over here by myself and draw a line, but I can't get to the right color, so I guess it's going to be in red. There we go. And there we go. And just so you all know, I am just sitting in my living room talking to myself. So that's 30 degrees, 25. That's the vector. That's the wind by itself. I have to, right now, take this and find the X amount and the Y amount. I am going to break it up into components. Now, this is why I spent all the time with all the vector stuff, all the triangle stuff. I see a triangle here with a 30-degree angle and a 25-degree angle. I have wrapped a right triangle around the angle. And I recognize this is going to be my adjacent side. This is going to be my opposite side. And let's see, this is my hypotenuse, so sine of 30 is going to give me the opposite side divided by 25. And cosine of 30 is going to give me the adjacent side divided by 25. Look up in my chart. Sine of 30 is 0.5 equals opposite divided by 25. So the opposite side is going to be 0.5 times 25. That's 12.5. The cosine is 0.866 equals adjacent divided by 25. So 0.866 times 25 means the adjacent side is 21.65. So 21.65. Now here's the hard part. I guess more the hard part. This is actually in the positive y direction. This is in the negative x direction. So I'm going to go back